Good morning, everyone. I hope you're having a good day inside the comforts of your home. By the way, I am Ruben Atuting, your reporter for today, and I'll be sharing to you the basic soil-water relationships. Learning the basic soil-water relationships has no better start than to know what is a soil composed of, how is it structured from within, if you look it from inside, and also what are the very important terms and formulas you will meet and see as you go along and study these basic soil water relations. Because later on, our aim is not only to know these informations, of course, but also to study further as to how water reacts as it penetrates the soil, and also how soil behaves as water goes through it. Soil is a thin layer of material covering the Earth's surface and is formed from the weathering of rocks. So if you go to your backyard and gather some soil sample, could be a soil strip, you're gonna end up seeing this one, what you have in your left side. So that is the natural state, normal state of water if you look at it. All the phases. So if I ask you what are the phases on this particular soil sample, probably you're gonna end up saying there are three phases, which is of course solid, liquid, and gas. So in this normal state, all the phases are arranged indefinitely. The solids are mixed up with water and of course the air, the gas, because of that force. You might ask that what are actually soil composed of? So I will tell you ahead that soil is composed of, that's it, solid, liquid, and gas. But what is solid composed of? Diba? You're talking about solid, and there are different types of solids like rock or metal, diba? But soil doesn't contain metal, right? So the soil is composed of minerals. So these minerals are specifically the clay, silt, and loam. Alright? So getting to know the fractions of composition of clay, how many percent are there, how many percent of clay is present on the soil sample, how many is loam, how many is silt. The fractions of those will tell you what is the soil texture. And that's it, no? Because in some instances, some will ask you that, usa man yung klase yuta, di ba? Buhi ba akong tanom ani? So, some yung pagtubag aron. So, you're gonna say to them the percentage of clay, the silt, and all those minerals. So, in order to do that, right now, this is what I'm talking about. The solids in the soil is basically the minerals that came from as a result of geologic weathering. So, what are the phases, or what is soil composed of? It is soil of solid, liquid, and gas. And what is solid there composed of? That is minerals. And where are these minerals came from? What are these? These minerals are clay, silt, and loam. And this clay, silt, and loam is just the minerals mixing up to the soil, to the remains of animals, animal residue or plant residue to form the soil. So these are the result of geologic weathering, if you ask. Alright? And the empty spaces right there. So if you go back here, these empty spaces is what they call pores or voids. So these voids is mainly composed of water and air. Ba? How much air, the volume of that air or the volume of that water composes the void, the pores. So the empty spaces are called voids or pores, occupied by either water or air, as written. And then the minerals, as I've said, the mineral solid fraction of the soil is made up of sand, silt, and clay. and the particular ratios of which determine the soil texture. And then going back, how do you determine if how many percent, or how can you say that this particular soil is clayey or loamy? Turns out that there is a study from Virginia Tech University that provides us a triangle, no, to identify the percentage, or that will, when you have the percentage, will give you the type of soil or the soil texture. So here you go. But for that, this is usually the sizes, the ice, sand, gravel, silt, and clay present in the solid phases of a soil. So for clay, it's about less than 0.002 mm, no, millimeters. That's very small. That's clay. Silt is about 0.002 mm to 0.05 mm. Sand is about 0.05 millimeters to 2 mm. Gravel is about 2 mm to 75 mm. And those greater than that can be considered rock. Diba? Di na daw na, wala na labot ang rock to identify what type of soil texture. So this is what I'm talking about, the soil triangle. So provided here on the left side of the triangle is the percentage of clay. The other side is percentage of silt. And in the bottom is percentage of sand. So, for example, no, you have 20% silt, you have 80% clay, and then, what else? You have 20% sand, yeah? Here you go, 20% sand, and then 20% silt, and then 80% clay. So you just have to trace from the numbers on the left or right or bottom. I-trace ra daw nimo antod moabot ka sa tunga, and then wherever you fall in that will give you the type of soil. So that particular soil we have an example 20% silt, 80% clay, and 20% sand will give us the soil texture which is clay. So that type of soil is clay. So this is how you identify the soil structure, or the soil texture of a particular soil sample. Alright. Soil texture determination is important because many soil properties are influenced by texture. So since we're talking about soil and water relationship here, it is important because it includes drainage, how the soil drains water when soil enters it, no? And then how it holds water as the soil stores some water in it, no? Water holding capacity, aeration, susceptibility to erosion, no? Kung kana bang type nga yuta, dali bang mabanlas or dali ba siya mo erode? Cation, exchange capacity, pH buffering capacity, and soil tilt. Now, going back to the figure, no, we have here the natural state. In natural state, diba, here's the fun part because this is now the technical part wherein we're gonna derive some basic formulas, because that formulas pertains or refers to the basic soil-water relationships. Alright, so you have here in the left side of your screen, this is the normal state wherein the phases are mixed up. You have the solid state, the liquid, the water, and the pores or the voids. Alright. In an ideal world, if you arrange that, the analogy here is somewhat like a 3-in-1 coffee bitaw, no? You have the creamer, the coffee, and the sugar. So that's the analogy. When you separate all of those, although it's hard, yes, it's hard because that's very tiny, huh? That's why it's called ideal world. So in an ideal world, we arrange them in a pattern in terms of its densities. So as you can see, solid, is pinakalalom because it's the most dense among the phases you can see in a soil sample. Followed by water, it's in the middle, and then the air at the top. It's the least dense among them. And then we label their volumes. That V, right there, volumes. The overall volume, the total volume is of course the volume of air, volume of water, and the volume of solid. Again, the volume of void or the pores. These are the pores. The gaps between the solid and liquid particles, liquid phases, or the water in the soil sample. That's the voids, which is composed of volume of air and volume of water. That's void. And then on the other side, we have in terms of weight. So the total weight of a soil is just weight of water and weight of weight of solid. Why do you think is that? It's because air, you can, if you weigh air, you're gonna have almost zero. The weighing scale will not actually move, or it might move, but very small and somewhat negligible. That's why we don't have weight of air right here. So ingon dire is it's just the weight of water and weight of soil or the solid that compose the weight of the soil sample. So that's it. So if it touches your interest and you wanna have the comparison, you wanna know the comparison between the voids and the solid, how much void in terms of solid, you're gonna end up having void ratio. Void ratio, or denoted as small e, is the volume of void divided by volume of solid. The more the void, the higher the void ratio. Because it's the numerator, diba? The higher the void, the higher it's either your volume of air or volume of water is more when you have higher void ratio. That's what it means. It's the volume of void all over volume of solid. That's void ratio. And then if you want to relate or how much void in terms of overall volume, the total volume, diba? Air, water, and solid. That's what they call porosity. Porosity denoted by letter N. And porosity is basically equal to volume of void all over the total volume. What's the analogy here? The analogy is this sponge. When you have sponge, when you have a sponge that you didn't squeeze yet, it has a lot of pores, right? So what does it mean? It's more porous because it's a lot of voids in it. But when you compress it, you squeeze it, you let go of those airs or even water on that one. And so those compact sponge is now less porous. Alright? So in connection with soil, when you have compacted soil, that's less porous compared to undisturbed soil. Alright? So you can see those what I'm talking about in this next slide, wherein we have the formulas. So again, if you just look into the figure, you have void ratio is equal to volume of void all over volume of solid. And for porosity, you have volume of void to the total volume. Volume of air, volume of water, and volume of solid. Then porosity, that's N. Volume of void over total volume. Yeah, that's what I'm talking about. And then degree of saturation is just the comparison of volume of water. Again, volume relationships, no? Volume of water to the volume of void. That's it for volume relationships. And then the void porosity equation. If you're given with either the porosity only or the void ratio lang ba, you're gonna have this formula. Volume of void, it came from here, no? By definition, volume of void over volume of solid. But this time, the volume of solid, instead of just saying volume of solid, they have overall volume minus volume of void. Because if you go back here, what's total volume minus volume of void? It is volume of solid, right? So that is why you have here volume of total volume minus volume of void. This yellow part here, diba? Hope you see it. And now what's going on? It the process is they multiply the numerator and the denominator by 1 over V or 1 over total volume. It's just an algebraic manipulation though. And we have what is volume of void over total volume? That's porosity, of course. Then on the denominator, that's V over V, so it becomes 1. And then again, volume of void over volume, total volume is porosity or N. So you're gonna have void ratio is equal to, in terms of porosity, you'll have porosity over 1 minus porosity. Or if you rearrange that, isolate porosity, you're gonna have void ratio over 1 plus void ratio. So these are the first relationships you're gonna have in terms of soil and water. That's void ratio, porosity, and degree of saturation. So here's a quick trick on how to memorize these various formulas for soil mechanics, no, and soil properties. Going back to the figure that we had a while ago, the mass of the air you can see in the particular soil is negligible, right? So you can, or we can say that, or we can assume that this mg is equal to 0, right? So this only means that in a soil sample, the mass of it is mainly composed of just the mass of water and the mass of solid particles present on it. Alright? So that also means that if air is nearly negligible, or let's say negligible in mass, then air must also be negligible in weight. So the weight of air is also negligible. Now, this is the mass. Now the formula is the total mass of the soil sample, M only, is gonna be equal to MS plus MW. So if katong una pa na nga na ay air, so plus MA. Pero since air has a negligible mass, this will just be the formula for mass. The total mass of the soil sample is going to be the mass of the soil, the solid, and the mass of the water. And then the density. So for the density, what is it? It's just rho. It is the ratio of mass over volume. So in our hydraulics, if maka-remember pa mo, the rho or the density of water is assumed to be 1,000 kilograms per cubic meter. That is the somewhat constant for density of water on a particular temperature and some instances, diba? Some specifications. This is the formula. Now for the specific gravity, no? Specific gravity na ta. We have here density of soil is going to be GS times density of water. Now what is this GS? This GS here refers to the specific gravity of soil. So again, tanang na subscript nga S that pertains to soil. Now, this specific gravity of soil is the comparison of weight of the solid in comparison to weight of water. And now, the formula will be for the specific gravity of soil, the density of soil is this one, which is also true by equating it to mass of solid over the volume of solid, because this is density, mass over volume. So this is just new formula for the rho of solid or the density of solid. Now let's move on to the different states. In analyzing or in studying soil samples, there are basic states that you will encounter. So for the soil that you just gathered from your backyard, that soil is going to be moist categorized as moist. Because if you observe that soil sample, it has somewhat wet and somewhat dry, or in the middle. So that's natural or moist. That soil is in moist. Now, when that sample, you put that in the oven and let it dry, completely dry, waterless, then that will be categorized as dry or oven dried soil sample. Oven dried state, moist, and then the opposite of dry is going to be saturated. Saturated state. Alright? Saturated state. And then the fourth category is submerged. It is still under saturated, but the only difference is your soil sample is being submerged. So of course, if that soil sample is submerged, it will be clearly in saturated condition. So for moist, the phases are just the normal phases. You have solid, you have water, and air. But when you dry that soil sample, you're gonna end up, or you're removing the water, all of the water there. So you're gonna end up having just soil and the air. Alright? Now, for saturated, which is the opposite, it is somewhat very wet, or you only remove the air, diba? You're gonna have soil and water. Soil and water only as your phases. For submerged, it is the same as saturated, that you have water and soil are solid. It's just being submerged. Now, for their saturation, degree of saturation. For dry, of course, its saturation is equal to 0%. But before that, what is degree of saturation? What does this mean? It's just simply the ratio of volume of water to the volume of solids. So, degree of saturation, which is S, denoted as S, is volume of water in comparison to volume of soil, or solid, volume of solid, right? So, when you completely remove the water, or the water phase in your moist sample, then of course, what will happen to the volume of water? You remove it, so it becomes 0. That's why you have 0% saturation on your dry category soil, the oven dried soil. Now for moist, you're gonna have saturation within greater than 0% but less than 100%. So 0 to 100% is your degree of saturation for your moist or natural category. For saturated, of course, it's completely wet, soaked in soil. You're gonna have 100% saturation. Here also, you have 100% saturation. So this is again another formula, no? Degree of saturation. This is in percentage. That's equal to volume of water to the volume of solids. And then you have water content. So for water content, it is noted as small w. It is somewhat the same to degree of saturation, a comparison to water or water to solids. But this time, you have the weight of water to weight of soil. Alright? So for degree of saturation, it's in terms of volume. While for water content or moisture content, another term is moisture content, you have weight. And since you're referring to weight, that can also be mass, yeah? Mass of water over mass of solid. You just remove the acceleration due to gravity since this is weight. Alright, that's water content and degree of saturation. Now, the next one is void ratio. So, E is equal to the comparison of voids, the volume of voids to the volume of solid. Diba? We already talked about it, that somewhat like a sponge. Diba? When you squeeze, you remove the void. Somewhat like that. So, that's the ratio of void, volume of void to the volume of solid. Well, for porosity, it's volume of void in comparison to the overall volume. So, this overall volume or the total volume includes the air, water, and solid phases. Alright, that's the formulas. Now, for the next category, which is the unit weight gamma. We have again different conditions. We have dry. For the formula for unit weight for dry, diba? You have gamma D equals GS, the specific gravity times the unit weight of water all over 1 plus E. But before that, let me discuss first the very important formula, also famous formula, which is the specific gravity of soil times moisture content, and that is equal to void ratio times degree of saturation. Alright, this is another formula. So, dapat din siya. So, this is it. The unit weight for water. So, for the derivation of this, how are these formulas derived? You can see the reference below. You can check out that. And you're gonna see that book. It has formulas there. But for now, let's just absorb these formulas. So, for unit weight, you have this. For dry, you have GS, gamma water over 1 plus the void ratio. For moist condition of the soil, we have unit weight moist condition is, that's still the formula. You just have to copy that 1 plus A. But now, you have to multiply it by 1 plus the moisture content. Alright? The only difference is you add 1 plus W multiplied to the term, the original term. Now, for saturated, this is for saturated, you have the same formula, saturated. The same formula, GS, the unit weight of water over 1 plus E, 1 plus the moisture content. And what's different? This moisture content must be, the S there must be in 100%. 100% moisture content dapat ay ang S. So, to achieve that, given this specific gravity in the problem, moisture content, you have this S must be 1. And then you have to calculate this W. May butang dire. When the condition is saturated. When the problem specifies that it is saturated. Now, for the submerged, this is the only difference. For submerged, you still have the formula. This is the notation for submerged. It's just the gamma saturated, unit weight when it's saturated, minus unit weight of water. That's it. These are the formulas you can use or you wish to memorize in dealing with soil properties and soil mechanics. Because these formulas are very important in especially board exams. The soil mechanics, magawas na siya. Right? This. Added this. So, these are the formulas. You have mass. Of course, the mass of the soil sample is just basically the mass of the solids plus the mass of the water. Right? For density, it's just mass over volume. For density of water, it's 1,000 kg per meter cube. For specific gravity, we have new term, which is the specific gravity of soil. Alright, so the density of solid can be now in terms of specific gravity times density of water. Or that is the same as mass of solid over volume of solid. For the different state, we have dry. That is when you remove all the water on that soil sample you have. So you end up having 0% degree of saturation. And again, degree of saturation is the volume of water over volume of soil, the comparison. So of course, when you remove all the volume of water, you have 0% degree of saturation. And then moist condition, when you have all the phases or the natural state of solid, water, and air, that's 0 to 100%. In between only. Because 100% is for saturated condition. Your soil is saturated and then submerged. And then W, of course, is moisture content or water content. You can have it as water content. So it's just the weight of water over the weight of solids. Comparison lang nila. Of course, the higher your water content becomes higher when there is more water compared to soil. Or the weight of water is heavier compared to soil. It is somewhat connected to the number of water and soil present, di ba? Kay mudagan imong water, mas mubugat man pud na siya. As in terms of mass, ikuhaon na to nimo tong acceleration due to gravity. And then the void ratio. The voids are the volume of air and volume of water all over the volume of solid. So tanan na subscript na S that solid void ratio. And then the porosity, N, which is equal to volume of void over the total volume, air, water, and gas. Air, water, and solid. Then the unit weight, kaya may importante. For dry condition, this is the formula. Specific gravity times unit weight of water. So you can have it as 9.81 in SI units. All over 1 plus void ratio. For moist condition, you have unit weight of soil when it's moist. You have specific gravity of soil or of solid times unit weight of water. All over 1 plus E. And the only difference is you add the term 1 plus moisture content. For saturated, the same, but only moisture content because the S there must be in 100% because it's saturated. For the submerged condition, you just have to subtract the unit weight of water from the saturated condition. So you're gonna solve that in you're gonna have to solve it first, that unit weight of soil in saturated mode, before getting the overall unit weight when it's submerged. And then, since we're talking about the relationship of soil and water, we should not forget soil structure. Because soil structure, or how these soils or the solid particles are arranged inside the soil, is important so that it will lead us to know how the soil contains water, how it stores. And there are basically 6 primary soil structure. We have platy, prismatic, columnar, blocky, single grain, and granular. So, soil structure refers to the arrangement of soil particles, and the aggregation of soil particles can occur in different patterns. So these are the patterns mentioned a while ago: platy, prismatic, columnar, blocky, single grain, and granular. For platy, it is made up of soil particles aggregate in thin plates or sheets piled horizontally in one another. Prismatic, you can see it in the picture. The units are bounded by flat to rounded vertical faces. Granular, pinong grains type of soil or arrangement are individual particles of sand, silt, clay grouped together in small, nearly spherical grains. Columnar are the units. The units are similar to prisms and are bounded by flat or slightly rounded vertical faces. You can see it in the picture. That's how different from each other. And then blocky are soil particles that cling together in nearly square or angular blocks, having more or less sharp edges. And then again, single grain, it's much fine compared to granular. Means there is no cohesion between soil particles, such as sand at the beach. Right? So you can see that is the 6 primary soil structural classes. Now, why is soil structure important? So it turns out that soil structure affects the rate that water and air can move through the soil, root penetration, and the availability of nutrients to plants. If your soil is more structured, like near with each other, of course it can trap water more than comparing it to soil that are far away from each other, structured far away from each other. So in single-grained soils like sand, water percolates very quickly through the soil. When in massive soils such as dense clays, water movement is very slow. Well-structured soils are usually more desirable for agricultural. Since our subject is about irrigation, it's of course connected to agricultural purposes. So that's the purpose of conveying water from reservoir to the plantation. And that's why we're here to study the soil and water relationship. Soil can hold and conduct water and gases and are also able to support load-bearing activities such as field traffic. So we have here soil bulk density and porosity. So bulk density expresses the ratio of the mass of dry soil, no? Dry soil to the volume occupied by it. It is necessary for it because it is an indicator of soil's porosity. So they're somewhat connected. And again, porosity is just the ratio of volume of voids to the total volume. Diba? Soil porosity is influenced primarily by soil aggregation, soil texture, root penetration, and other biological activities. So ano naman dahil if ang soil is porous or ang soil ba is less porous? Diba again, for the sponge analogy, when you have more porous, means it has more voids in it. So, what happens? Could either be sudlan siya og mga wati, which is good for the plants, di ba? And for the in terms of water, if you have less porous, so nang gawas na tanang water, it drains out all those nutrients, di ba? Because in most farmers, if you observe them, they prepared or they till ilang kutaon gyud ang yuta sa sila magtanom because those soil will support more plant growth compared to bantok. Pag bantok gaya mong yuta, wala kay ng tubig ana, kay mo squeeze man, mo go out na ng tubig. So that's soil bulk density and porosity in terms of, in relation with water and how soil reacts. Then we have micropores and macropores. This is the pores or the holes inside your soil. We have when micropores, that's 0.08 mm or smaller pores. And then macropores are those larger than 0.08 mm. So what does micropores and macropores brought? So it affects how water passes through the pores, and it affects how the soil stores water. When you have very fine pores, then you're gonna store more water. Yeah. So that's it. And then according to a study from Virginia State University, they come out with a graph here, no? On the x-axis, they have the soil texture, and on the y-axis, they have water content percentage by volume. So according here, not all plants or not all water that goes through the soil can support plant life growth. Muna siya kamatuuran diya. So we have the region here that only support the water that only support plant life growth. So that's the term there, they call it plant available water. So the field capacity, you have here the definition of field capacity is the amount of water that remains in the soil after 48 to 72 hours. So they study the type of soil. We have sand, sandy loam, silt loam, clay loam, silty clay, and clay. That's all their samples. So they try to put water in it, compared it, no, and they let the water stay on that soil for 48 or 72 hours. And then they found out that the sand holds water very quick. Dali lang mamala. Di kay siya mukuag water. Ba? As you can see, dual siya sa 0. Alright? And the clay being farthest, mudang mo'y dugay na malayan. Nakastore siya og water more. Available water, as I've discussed, is the only remaining amount of water that can support plant growth. Diba? Again, dilitan ang water makakuha ng plant growth. And the wilting point is the minimum moisture content of the soil that can support plant growth. So here, based on the graph, makita niyo, the wilting point of loam is around 16. There is the pit, 16. Then its field capacity, narin ni the pit. So, bye-bye siya og plant available water for So, Virginia State University also tabulate the result. So, muna yung nigawas nga result. For average available water content na lang daw for various soil textural classes. So, if mabantayan ninyo diri sa table, ang somewhat, if ako ipa-decide on, ang the best nga soil for plants is either loam, silt loam, or clay loam type of soil. Kaya ano, because its available water is significantly or relatively higher, 15, 21, and 20 compared to sand. Diba? And plants really need water that can make them grow and stay alive, diba? So Arikas, more available water. And also, look at their field capacity or moisture content. Importante na siya makahold siya water because water is important to plants because plants need water in photosynthesis and making their own food so that they can grow. When you have very low moisture content or percent moisture, field capacity in your soil, bati kay na siya, dili na maka-grow og plants kayo. Wala, inyo ang based on experience. Nakabantay na ba mo og mga farmers nga magtanom sa mga beach, like sandy man na diha nga type of soil? Ba, wala kayo. Wala kayo farmers magtanom sa sandy. Ang lagmit ra nga buhi sa sandy type of soil are sometimes kalamunggay. Yeah, wala siya ng buhi diha. And then their wilting point is significantly higher pod if i-compare lang yun nimo ang clay loam, di ba? Clay loam to sand. Sand got 5 only. Diba? And 24. So this is how soil and water are related to each other and how plants benefits from the ability of soil to hold water, contain water, and drain water. And also those relationships. So as a sort of summary, soil is related to water in terms of how water reacts as it penetrates. The basic relationships of soil and water, of course, can be quantified by volume relationships, void ratio, porosity, degree of saturation. Because from that, you can decide and study further what is the best soil for your specific plants. And then weight relationships, unit weight, moisture content, specific gravity. And then plus katong formulas nga akong gihatag, gi-explain sa inyo. And then the additional relationships are soil's ability to store water, katong nasa table and graph. And soil's ability to hold water. So that wraps up our presentation for today. Thank you so much for listening, and I hope you got something today. Peace out. Thank you.